Welcome to lecture number 4 for ECE 341, Random Processes. In this lecture, we're going to look at combinatorics, and the specific case we'll look at is 5 cards stud poker. Now, before we start, let's do a couple definitions. Combinatorics is how many ways an event can happen. What we did in the previous lecture is do enumeration, just go through every combination and count how many times that happens. That does work, but sometimes there are just too many possibilities. In those cases, you can actually calculate how many possibilities there are. But to do that, we'll need to use a couple things like factorials, permutations, and combinations. Now, a factorial is a product of a number and all the numbers smaller than it. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. We'll define 0 factorial to be 1, just to avoid divided by 0 in some cases. P of x is the probability of outcome x. Now, there's permutations and combinations. If I have n pick m, that's permutations of n events taken m at a time. And choose m and cm is combinations of n events taken m at a time. Combinations is also written as parentheses nm. The formulas for those are n pick m is n factorial over n minus m factorial, and choose m is n factorial over m factorial over n minus m factorial. We'll talk about those a little bit later this lecture. And there's also sampling with replacement and sampling without replacement. If I have a bunch of marbles, I pull a marble out and I leave it out. That's sampling without replacement. If I take a marble, take it out, then put it back in, that's sampling with replacement. When I sample with replacement, the odds don't change trial to trial. When I take out a marble, the odds do change each trial. Eventually I run out of marbles. So those are a couple definitions. Now, this lecture kind of picks up where we left off last lecture. Last 2 lectures we looked at Monte Carlo and enumeration. With Monte Carlo, if I can write a program to play a game 1 time, I can play it 1,000,000 times, and then just count. How many times does the event happen, like I roll 3 6s? Monte Carlo will get you a number that's close, almost right, but because it's a random process, I get a different answer every time. I can run it multiple times and get a better idea what the actual probabilities are. That's a t-test, a topic coming up later in this course. Enumeration also works. Enumeration is where just a brute force go through every possible combination and count how many are successes. The nice thing about enumeration is the answers are exact, and MATLAB works really well for enumeration. Typically I have a bunch of nested for loops. However, sometimes enumeration just takes too long as well. A third approach, what we're going to talk about today, is combinatorics. I can calculate the number of ways to get a given outcome. Like enumeration, the answers are exact, but I don't have to run a program over and over and over again in nested loops. I can just calculate the answer. Now we're going to be talking about permutations and combinations. Permutations is sampling without replacement when the order matters. So for example, suppose I've got 20 people lined up to play volleyball. How many teams can I make out of 20 players? In this case, order matters. So a volleyball team consists of 6 players. If I pick them saying the first player is the strong side hitter, the second player is the middle hitter, third one is the weak side hitter, fourth one is back row specialist left, fifth one's the setter, sixth one is the back row specialist right. Order matters. In that case, the number of ways to do it are as follows. The first player picked, there are 20 players to choose from, that's 20. The second player picked, there's only 19 remaining. After that, 18, 17, 16, 15. There are 27,907,200 different ways of forming a volleyball team out of 20 players if the order matters. Now that is written as 20 pick 6, or 20 p6, or 20 factorial over 20 minus 6 factorial. So kind of the way that works, 20 factorial are all numbers from 20 down to 1 multiplied together. 20 minus 6 is 14. That's 14 times 13 times 12. When I divide, all the terms from 14 on down to 0 cancel, and I'm left with the numbers that are different, 20 to 15. So that's another way to write 20 pick 6. Now combinations is sampling without replacement where the order doesn't matter. So for example, if I'm going to pick 6 players and they can reorganize themselves as to who plays what position, it doesn't matter how I choose those 6, they're going to rearrange themselves. Or in cards, if I can take my hand and shuffle it, order doesn't matter, that's a combination. As an example, if I have 20 players trying out for volleyball, the number of teams I can arrange or make where order doesn't matter, well, the number of teams where order does matter is 20 pick 6. If the order doesn't matter, then I'm overcounting by 6 factorial. I've got 6 players on the team, so the first player can be any of those 6. The second one could be any of the remaining 5, and so on. So 20 choose 6 is 20 pick 6 divided by 6 factorial. There's 38,760 different ways to form volleyball teams of 20 players. I can also write that as 20 choose 6, or 20 choose 6, or 20 factorial over 20 minus 6 factorial over 6 factorial. However you do it, the answer is 38,760. So let's do a couple examples of combinatorics. And to give an example, let's look at 5-card stud poker. Now the way poker is played is you start out with a deck of 52 cards, you shuffle the deck, then the first card is dealt face down so that only the player can see it. The second card is dealt face up so everyone can see it, and there's a round of betting. Once betting's over, the next card is flipped over. Then the next, then the next. Once all 5 cards are dealt, betting is finished, you flip over your card, highest hand wins. That's 5-card stud. And there's a lot of variations. There's 6-card stud, there's Texas Hold'em, there's 7-card stud, all variations on that. We're just going to focus on 5-card stud in this lecture. On the homework sets, you might get other games like 6-card stud, 7-card stud, but that'll be in a homework set. So let's calculate the probability of getting different hands, and let's use combinatorics to come up with those answers. Now in poker, the rank of hands are as follows. The best hand you can get is a royal flush. That's the 10, jack, queen, king, ace of the same suit. Followed is a straight flush. That's a run of 5 cards in the same suit. That's both a straight and a flush. Next is 4 of a kind. That's like 4 jacks and an off card. Full house, I've got 3 of a kind and 2 of a kind. So for example, 3 jacks and 2 queens would be a full house. A flush is the value doesn't matter, they're all the same suit. Like 5 hearts would be a flush, 5 spades would be a flush. Straight is a run of 5 cards. So that's ace, 2, 3, 4, 5, 7, 8, 9, 10, jack. You have 5 cards in a row. Oddity about straights, aces can be high or low. So the ace could be a 1, ace through 5, or it could be high, 10 through ace. 3 of a kind would be, for example, 3 cards that match, 2 that don't match. If these 2 did match, that would be a full house. 2 pair, I've got, say, jacks, pair of queens. This is an off card, doesn't match any of them. If X did match one of them, that'd be a full house. And the jacks and queens can't match. If they did match, that'd be 4 of a kind. Pair is I have 2 cards that match, 3 off cards. And high card, meaning no matches, no straights, no flushes. So that's the rank of hands in poker. In order to get the probability of each type of hand, one way is to go to Wikipedia. Now, poker's been analyzed to death, and we know very well how many different ways can you get a straight flush, how many different ways you can get 4 of a kind, and so on. That's all in Wikipedia. And here the straight flush also includes royal flushes. Well, the total number of hands is 2.5 million, so the probability, assuming all hands are equally likely, say for straight flush, would just be 40 divided by 2.5 million, which is 69,974 against. So this is what I can find from Wikipedia. If I do enumeration, I'll get exactly the same answer, except it'll take me about 2 minutes to run the program. That's what we did last lecture. Using enumeration, I can do a bunch of nested for loops. I have 5 cards. The first card could be any card in the deck. The second card can be any card starting from the previous card plus 1. So if I just list the cards as being cards number 0 through 51, or 1 through 52, the first card could be card number 1. The second card dealt can't be number 1. I can't have 2 identical cards in the same deck. I'll start from 2. The next card will be the next one plus 1 and so on. We talked about that last lecture. Go through every possible hand. There's 2.5 million hands you have to go through. For each hand, I'll write a program and count. As I go through all combinations, is that hand a straight? Is it a flush? Is it 3 of a kind? Count, and I'll get exactly the same answer that I get with Wikipedia. That's enumeration. A third approach, which is what we're talking about today, is combinatorics. Can I calculate the number of ways to get each type of hand? Now, the answers I get should match the answers we got before. I mean, those answers are exact. Combinatorics should give you exactly the same answer as well. The nice thing about combinatorics, though, is it takes a lot less time, but it can be kind of tricky. Now, in terms of time, it takes about 2 minutes to run the program in MATLAB that goes through every hand. That's for 5-card stud. If I play 6-card stud, it's going to take about 100 minutes to go through every combination. 7-card stud, what would that be? Well, it's going to take about 2 weeks to go through every combination. Eventually it just gets too long. So enumeration has got limitations. Sometimes there's just too many combinations. That's where combinatorics comes into play. I can calculate how many hands there are. So let's start out with how many different ways can I shuffle a deck of 52 cards. Well, when I do that, the top card on the deck has 52 possibilities. The next card has 51 possibilities. The next card has 50, and so on. So the number of ways I can shuffle a deck is 52 times 51 times 50 times 49 times 48, all the way down to 1. That's 52 factorial. Most calculators have a factorial key. MATLAB has factorial, spelled factorial. If you type that out, that's 8.06 times 10 to the 67th power. So kind of note that there are way too many combinations, even for a computer to run through, all possible ways to shuffle a deck. Let's go through some permutations. Now, suppose the order matters. So for example, I'm going to deal out a poker hand. That's a hand of 5 cards. If the order matters, such as I've got the first card, then the second card, the third card, that'd be like 5-card stud. How many different ways can 5-card stud play out? In that case, order does matter because the order that you get the cards affects how the betting goes. If order matters, then the number of hands possible would be just 52, 51, 50, 49, 48, then you stop. You only deal out 5 cards. That is 52, pick 5. There's 311 million different ways a game of 5-card stud could play out. That's if order matters. What we're going to be doing is combinations. Order doesn't matter. For example, I deal out 5 cards and I can shuffle them. Or when I'm done, it doesn't matter the order. If I have 3 aces, that's 3 of a kind, no matter where they are in my hand. If order doesn't matter, that's actually combinatorics, combinations. So with combinations, I overcounted each hand by 5 factorial. So if I take the permutations divided by 5 factorial, I get combinations. Or another way to write it is 52 choose 5, or 52 choose 5. That's the number of hands of poker when order doesn't matter. That works out to 2.5 million hands. And notice that's exactly the same number we got with enumeration. When I ran through every possible hand, that's the same number I got. 2,598,960. But I calculated it. So let's start going through the odds of getting different hands. The easiest is a royal flush. A royal flush is when you have 5 cards of the same suit going 10 through ace. That's a straight and it's a flush, so it's a straight flush, but it includes all the royalty: ace, king, queen, jack, 10. In this case, enumeration works really well to calculate the number of ways to get a royal flush. There's just 4 of them. I can list them out. I can have a royal flush in clubs, diamonds, hearts, and spades. That's 4. So that one's pretty easy. The probability of a royal flush is the number of hands that are a royal flush, 4, divided by the probability. That gives you the number from Wikipedia, odds against a royal flush. So using enumeration, it's just 4 over 2.5 million, or 1 hand in every 649,740. Meaning, if I played 649,740 hands of poker, on average, I'll get 1 royal flush. So they're not really likely. Can happen, but not very likely. Let's look at 4 of a kind. Now, from Wikipedia, or enumeration, there are 624 different ways to get 4 of a kind. How do you compute that? So what I kind of suggest is pause the video, think about it, and then when you're ready, start it up again. So to calculate it, I've got 4 of a kind, so I've got 4 cards that match, call those X's, and I have another card that doesn't match. That's what 4 of a kind looks like. So kind of one way to do that, I've got 13 cards in the deck, ace through king. I'm going to, of those 13 cards, choose 1. That'll be what X is. And then in the deck, there are 4 X's. Choose 4. That takes care of the X's. For the off card, there are 12 remaining cards in the deck. In this example, I chose kings. I picked out kings, the 4 kings in the deck, I pulled them out. That's my 4 of a kind. This 10, the off card, there are 12 cards that are not a king. 12 values. Pick 1. And of the, say in this case 10s, of the 4 10s in the deck, pick 1. Multiply all that out, I get 624. So that's actually the way you calculate 4 of a kind. Again, the cards, I've got 13 different values, pick 1. Of the 4 kings in the deck, pick 4. Equally valid way of doing it is of the 48 remaining cards, again there's 52 cards in the deck, I take out 4 of them for the kings. There's 48 other cards, pick 1 of them. That's also the same way, same thing as 12 values, pick 1. 4 cards of that value, pick 1. Either way you calculate is correct. Get the same answer, 624. So that's the odds of being dealt 4 of a kind. 1 in 4,165. Let's take the next one. 3 of a kind. Now 3 of a kind looks like this. I've got to have XXX AB. From enumeration, the total number of ways of doing that are 54,912. How do you calculate that? Again, pause the video and see if you can solve that. Okay, so here's one way you could do that. Again, there are 13 different values, ace through king. Pick 1 for X. There are 4 X's in the deck. Choose 3. That takes care of this guy. Now, what I could say is there are 12 values that aren't X. Pick 1 for A. There are 4 A's in the deck. Pick 1. And there are now 11 values for B. Pick 1. There are 4 B's. Pick 1. So let's calculate that. Now in MATLAB, I'm going to need an nChooseM function. So this is creating a function nChooseM, so I can now use it. In MATLAB, I can then say, okay, n is nChooseM of 13 choose 1 times and choose m of 4 choose 3 times and choose m of 12 choose 1 times and choose m of 4 choose 1 times and choose m of 11 choose 1 times and choose m of 4 choose 1. I should get 54,912. And I'm off by a factor of 2. That's not the right way to do it. The problem I have is if I make this 10s and 3s, I double counted them. I also have 3s and 10s. With combinatorics, the trick is if I have two numbers that are the same frequency, I handle those together. So that's the wrong way to do it. The right way is there's 13 choose 1 for x, 4 choose 3, that's okay. But now, since a and b both have the same frequency, there's one of them, I have to say there are 12 remaining values, choose 2 of them. That pulls out a and b. There are 4 a's, choose 1. There are 4 b's, choose 1. So now when I do it that way, I'll have 12 choose 2 times 4 choose 1. That gives me the a's. 4 choose 1, that gives me the b's. There's the right answer. And that's kind of a recurring theme. If you have two numbers with the same frequency, calculate those together. And that's the right way to get 3 of a kind. So the odds of a 3 of a kind, there's 54,912 hands that are 3 of a kind, 2.5 million total hands. The ratio is 1 in 47. For every 47 hands you're dealt, on average, you'll get 1 3 of a kind. How about a flush? With a flush, you've got 5 cards of the same suit. What's the probability of getting a flush? Again, pause the video, see if you can calculate that. Okay, starting out, flush is 5 cards of the same suit. If I include straight flushes and royal flushes, just say all flushes, then what I would have is there are 4 suits, choose 1. There's clubs, diamonds, hearts, and spades. Pick one of those suits. If I picked hearts, then there are 13 hearts in the deck. Pick 5. That's almost the right number. From Wikipedia, the number of straight flushes is 5108. If I tried that in MATLAB, that'd be, and choose m, 4 choose 1, times, and choose m, 13 choose 5, 5148. I am off by 40. Well, the reason I'm off by 40 is there are 40 straight flushes. So a straight flush can start from the ace, the 1, through 5, all the way up through 10 through ace. So there's 10 straight flushes. Times 4 suits gives you 40. So take that number minus 40. Those are the straight flushes. And I get 5108. That's so many different ways you can get a flush. Note that it helps to know the answer to find the answer. So here's all the flushes, including straight flushes. Take out the straight flushes and royal flushes, I get 5108. The odds against being dealt a flush are 1 in 504 hands. Let's look at a straight. A straight is 5 cards in a row. So ace, 2, 3, 4, 5, 5, 6, 7, 8, 9. Okay, the first card I pick. The first card could be anything between ace to 10. So there's 10 values, 4 different suits. So there are 40 different cards I can choose for the first card. Once I pick that first card, the next card has to be, like in this case if that was a 5, I'm going to say there are 4 6s in the deck, choose 1. Then the next card, there are 4 7s in the deck, choose 1. 4 8s in the deck, choose 1. 4 9s in the deck, choose 1. So let's multiply that out. The number of straights then is 40 times, and choose M, 4 choose 1, and there's 4 of them, 10,240. Okay, that's close. I want to get 10,200. I'm out by 40. Well, the reason I'm out by 40 is, again, the straight flushes. There are 40 straights that are also flushes, so subtract out 40. Get 10,200. That's how many straights there are. And sure enough, that's how you calculate the number of straights. So the odds of getting a straight are 10,200 divided by 2.5 million, or 254 to 1 odds against. Two pair. Try to calculate the number of ways to get a two pair. Okay, so again, x and y is the same frequency, so we need to calculate those together. So the number of hands that are two pair, there's 13 different values. Choose 2. In this case, I'd pull the queens and sevens. Now there are 4 queens in the deck. Choose 2. There are 4 sevens in the deck. Choose 2. Now the remaining card, there are a couple ways of doing this. There are 11 different values that I haven't picked. Choose 1, and 4 cards of that value, choose 1. I could also just say times 44. There are 44 cards in the deck that are neither queens or sevens. Of those 44 cards, choose 1, same thing. If I multiply all that out on MATLAB, that'd be and choose M, 13 choose 2 times and choose M, 4 choose 2 times and choose M, 4 choose 2 times 11 times 4. 11 choose 1 is just 11, 4 choose 1 is just 4. Save a little bit of typing. 123,552. Boom, got it. So that's how you calculate the number of ways to get two pair. Or about 21 to 1 odds against getting a two pair. Single pair. Again, kind of note, I've got 3 at the same frequency. So to do that, I'm going to first find the number of ways to get a pair. There's 13, choose 1. There's 4 x's in the deck, choose 2. So that gives me the x's. A, B, and C have the same frequency, so I need to do those together. There are 12 other values, choose 3. That pulls out A, B, and C. 4 A's, choose 1. There's 4 B's, choose 1. 4 C's, choose 1. Multiply all that out, I get 1,098,240, just what Wikipedia had. That's how you get one pair. Again, kind of notice, if they're the same frequency, I need to calculate those together. So using combinatorics, I can get exactly the same answer I got with enumeration or Wikipedia. Now, where this really shines is, suppose I had a different game. Instead of doing 5-card stud, I did 6-card stud. Odds change. If I do 7-card stud, you're dealt 7 cards. What's the best 5-card hand with 7 cards? Odds change. What if I shuffled 2 decks together? What are the odds? Well, let's look at the last case here in the lecture. On the homework sets, we might do some of the other different possibilities. Here I want to look at a deck of 104 cards. Basically take 2 decks of cards, shuffle them together. Now what are the odds? The odds are going to change. If I deal out 5 cards, how many hands can I deal? Well, if I have 104 cards, well, let's go back to here. the number of hands I can deal. I can do that in MATLAB. That'd be, and choose M. There's 104 cards in the deck. Choose 5. There's now 91 million different hands. This is kind of where enumeration just is not going to work. It was 2.5 million hands with a single deck of cards. 91 million, basically 45 times more, with 2 decks of cards. Something that used to take me 2 minutes to grind through with enumeration is now taking me 90 minutes to grind through. I don't want to sit there and have a 90-minute video just watching a program run. I actually don't want to sit there and wait 90 minutes. I need a better tool. That's Combinatorics. So there's 91 million hands. How many different hands have, say, 4 of a kind, 3 of a kind, and so on? Let's calculate that. So what are the odds of getting 4 of a kind if I have a 104 card deck? Again, what I'm going to do is there are 13 values. Choose 1. Say I chose 10s. Now there are 8 10s in the deck. Choose 4. You can actually get 5 of a kind in a 2-deck and dual decks. 5 of a kind, I think, is higher than Royal Flush. I'm not positive, but so anyway, here's 4 of a kind. There are 8 10s in the deck in a double deck. Choose 4. There are 48 remaining cards times 2. Let's do it this way. There are 12 cards that aren't 10s. Choose 1. There are 8 cards of that value. You say 8 8s. Choose 1. That's how many different hands should be 4 of a kind. If I do that, this would be pair 4. I'm doing it this notation. MATLAB doesn't allow you to have a number in front of a variable. I can't say 4 pair. It has to be a letter. So this is pair 4. That means 4 of a kind. That's going to be 13 choose 1. That's just 13. Times and choose M of 8 choose 4. Times 12 times 8. And 12 choose 1 is 12. 8 choose 1 is 8. There should be 87,000 different ways of getting 4 of a kind. And the odds should be 1,052 to 1 odds against. Now comparing, the odds actually got better. 4 of a kind used to be 600 to 1 odds with a single deck of cards. With 2 decks of cards, it is now 1,000 to 1 odds. Actually, the odds got worse. Calculating. Again, here's how many different hands there are. 104, choose 5. Here's how many ways to get 4 of a kind. There's 13 different values, choose 1. 8 of those cards, choose 4. 12 remaining values for Y, choose 1. Of those 8 Ys, choose 1. 87,000 or 94.99 to 1 odds against, I think. Must have a typo here. Anyway, that's what the odds are. Let's try full house. Again, a full house, I'm going to get XXX, YY. To calculate it, there are 13 different values. Choose 1 for X. There are 8 X's. Choose 3. For Y's, there are 12 remaining values for Y. Choose 1. Of the 8 Y's, choose 2. So the number of hands for a full house that's pair 3, 2. It's 3 of a kind and 2 of a kind. That should be 13 choose 1 times and choose M of 8 choose 3 times 12 choose 1 times and choose M of 8 choose 2. 244,000 different ways to get a full house. if you have 2 decks. Now the odds against MATLAB is case sensitive. 375 to 1 odds against. Again, comparing it, a full house is 375 to 1 odds against. Actually got better. It was 4,000 to 1 odds, now it's 1,000 to 1 odds. It was 694 to 1 against, it's now 375 to 1 against. So the odds are actually getting better when you have 2 decks of cards. 2 decks of cards do affect the odds. That's a full house. And here's the number of hands. Here's the X's. 13 choose 1, 8 choose 3. Here's the Y's. 12 choose 1, 8 choose 2. 265 to 1 odds against. I gotta work on my some typos in here. Okay, so how do you check your answers? Well, enumeration just takes too darn long. If it takes 30 minutes for a 52-card deck, it's going to take 16 hours for a 104-card deck. So I can't do it that way to check my answers. I can do Monte Carlo. So with Monte Carlo, what I'm going to do is take the previous program, and instead of dealing out shuffling 52 cards, I'm going to shuffle 104. So what that looks like is I'm going to take a 104-card deck, shuffle it, I'll deal out a 5-card hand, and then count how many different times, determine what kind of hand that is and count. Is it a 4 of a kind, 3 of a kind, 2 of a kind, and so on. The odds then will be approximately the number of times each hand has occurred divided by the number of hands dealt. So here's the procedure. I'm going to start with shuffling 2 decks of cards. So I'm going to, instead of shuffling 52 numbers, it's going to be 52 times 2, 2 decks of cards. I will then sort. What I care about is the sort order. This is the numbers 1 to 104. I'll subtract 1, so now it's 0 to 103. And if I do that, here's my, say, the first 10 cards. It's going to be different every time you do it, but the first card is card number 18, 69, 70, 47, and so on. So that's the cards in the deck from 0 to 103. Take that mod 52. Again, the cards repeat every 52 times. We have a deck of cards going ace of spades all the way through. Next deck of cards above it is also ace of spades all the way through. Repeats every 52 cards. So take the deck, mod 52, and this is card number 18, 17, 18, 47. Kind of note, there are 2 18s in the deck. I've got 2 decks. I could have 2 of the same card. I'll then draw a 5-card hand, or the top 5 cards in the deck. So here's my hand. Once I have my hand, determine the value in the suit. Now the hand, mod 13 plus 1 is the value. That's the numbers 1 through 13. Ace through king. The suit is the floor of hand over 13 plus 1. This is 1 to 4. Clubs, diamonds, hearts, spades. So for example, the hand that I dealt is the 6 of diamonds, the 5 of diamonds, the 6 of diamonds, the 9 of spades, the ace of diamonds. So actually, if I was playing poker, I'd probably go for diamond, go for a flush. But that's my hand. For pairs, I count the frequency of each card. So I'm going to go through my hand and count how many aces, how many 2s, how many 3s, how many 4s, just like before. I'll then sort in descending order so that n of 1 is the highest frequency. If the highest frequency was a 4, I had 4 of a kind. Next highest frequency, well, if the highest frequency was a 3 of a kind, and the second highest frequency was 2 of a kind, that's a full house. 3 of a kind and less than 2 of a kind is the 3 of a kind. Pair and a pair is 2 pair. Pair and nothing is a pair. So here's the entire MATLAB code. If I then run that, so here's what the code looks like. If I deal out 100,000 hands, it takes 3.6 seconds to run. And in 100,000 hands with 2 decks of cards, 104 card deck, I got 96 four-of-a-kinds, 278 full houses, so on. If I run this for 1,000,000 hands, Marcus gets that go. If I make this 1,000,000 hands, then 100,000 hands was 3.6 seconds. This should take 36 seconds. I let this run. It's grinding away. And 30 seconds later, I get an answer. Now, kind of notice I get different answers every time I run it. This time I got 938 four-of-a-kinds, 2645 full houses. That's in 1,000,000 hands. If I run it again, 30 seconds later, I'll get an answer. Pause the video so you don't have to sit there and wait for it. So there's the second answer. Again, note, with Monte Carlo, I'm going to get a different answer every time. It's a random process. It'll hover right around the actual probability, so it kind of gives me an idea what it is, but not an exact answer. That's Monte Carlo. I can do it. It takes a while, a whole lot better than 50 hours. The results of Monte Carlo, anytime you have a program, I want to test it. So if I change it to just dealing out a regular single deck of cards, I know what those odds are. Those are what we calculate with enumeration. Those are available on Wikipedia. I can compare the Monte Carlo results to the calculator results, and they seem to match up pretty well. Okay, that gives me some confidence that my program's correct. Now here's where the leap of faith goes. Let's deal 2 decks. With 2 decks, I have calculated 4-of-a-kind odds, full house odds. 3-of-a-kind, pair, 2 pair, we'll leave as a homework set. With the Monte Carlo simulation, here's the number of hands that were 4-of-a-kind, kind of matches up. Full house, kind of matches up. Not sure, not sure, not sure. If these are correct, these are probably correct. But kind of notice the odds change. They definitely change when you have 2 decks of cards versus 1 deck of cards. With Combinatorics, I can calculate those odds. Now there's other versions of poker as well. For example, this is 5-card stud. There's also Texas Hold'em where you have 6 cards. You get 4 cards for your hand, the dealer has 2 cards face up, and you can use, the other way around. You get 2 cards, the dealer has 4 cards, you can have any 5-card hand with a combination of those 6 cards. That's Texas Hold'em. There's 7-card stud. I have 2 cards dealt face down, 4 up, 1 down. Best 5-card hand of those 7 cards. You're dealt 7 cards. What's the probability to get 4-of-a-kind when dealt 7 cards, full house when dealt 7 cards, and so on? Again, we'll leave that as a homework set. You really can't use combinatorics, or can't use enumeration in games like those, just because there's too many combinations. But combinatorics will get you the answer dead on, if you do it right. So that's combinatorics. In summary, with combinatorics, you can calculate how many different combinations result in a given outcome. Here in this lecture, we looked at 4-of-a-kind, full house, 3-of-a-kind, things like that, with 1 deck of cards, 2 decks of cards. Where combinatorics is kind of nice is when there's a huge number of possibilities and enumeration just takes too long to go through. Combinatorics is a way to get the answer, and you should get exactly the same results, but you just calculate it. It takes just a few milliseconds rather than hours. And that's lecture number 4 for ECE 341, Random Processes, Combinatorics.